In this video, you are going to see how can we apply the knowledge of dimensions to check the correctness of a given physical relation. Here also you will use what is known as principle of homogeneity of dimensions to check whether a given physical relation is dimensionally correct or not. I have already told you before, if the terms in every equation, like for this, if the terms in this equation, all the terms, if they have same dimensions, then we are going to say that this equation is dimensionally correct. But however, if the terms they do not have same dimensions, then I have to say that this equation is wrong. So let's check the first one, example 1, where this is the equation given, where S represents displacement. The dimension of displacement is L, length. Then we have to find the dimension of this term here, which is ut. So dimension of ut means dimension of velocity into dimension of time. Dimension of velocity is Lt minus 1. Dimension of time is simply t. When I take this t to the power minus 1 and this t, which is power 1, I'm going to get t to the power minus 1 plus 1, which is t to the power 0. T to the power 0 means there is no time. So this equation or this dimension of this ut is simply L. Now the final term, that is your half at square. Half at square, this half is purely a number, it doesn't have dimension. So we simply have to multiply the dimension of a, which is acceleration, with dimension of time square. Dimension of acceleration is Lt minus 2. Dimension of time is t, so we have t square. This t square and this t to the power minus 2 is going to give you a power of 0 for the t. So we simply have again L. So you saw just now the dimension of each and every term are same. Hence, I can say that this relation which has been given to us is dimensionally correct. Next, suppose we have an equation which is your E equals mc square. This is your famous Einstein's equation where E represents energy, m represents mass, and c represents speed of light. So to check whether this relation is dimensionally correct or not, we are going to write the dimension of energy, that is also the dimension of work, and we know it is equal to ml square t to the power minus 2. Now we are going to check the dimension on the right hand side, that is your mc square. For that, we are writing dimension of mc square is equal to dimension of mass dimension of c square. Mass is simply your m. C is speed. Speed or velocity, they have a dimension of Lt minus 1. We have this square, so we have this square over here. This square with L becomes L to the power 2. T to the power minus 1 into 2 will become t to the power minus 2. So you can see we have got dimension of mc square as well. So you can see now dimension of E is same as dimension of mc square. That means all the terms on the left hand side and right hand side have the same dimensions. So I can say that the given relation, that is your mc square, is dimensionally correct. Let's check the next example where we have been given t as the time period of a simple pendulum. Then we have this 2 pi root over L, which represents length of the simple pendulum. So actually this L is the effective length measured from this point to the center of the bob of a simple pendulum, and g here represents acceleration due to gravity. So we have to check whether this formula is dimensionally correct or not. To do that, as usual, we are going to find the dimension on the left hand side, that is your time period, and time period simply represents time measurement, so the dimension is time. Then the dimension on the right hand side, that is your 2 pi root over L by g. 2 pi does not have dimensions, so I can ignore that. So we must write the dimension of root over of L over g. That simply means root over L by dimension of root over g. Now L means length, so I have written here length. This square root means power half, so I've written L to the power half. And then this g here, if you remember, is your acceleration, and acceleration is meters per second square. So we have L to the power minus 2. And this root here that we have with g is going to have everything as power half. So we still have this L as power half. This L here also has this power half, so we have written L to the power half. This t square, that is your minus 2 power, has also the power half. This 2 and this 2 gets cancelled because we are multiplying this 2 minus 2 with half. So this 2 and 2 gets cancelled. So we simply get minus 1. So we have this t to the power minus 1 remaining here. And this L half in the numerator, and we have L half in the denominator. So we can write L to the power minus half or L to the power 0. So we do not get any L. This t can go up here and become dimension of t. So we got the dimension on the left hand side as your t, and even the dimension of all this term that is on your right hand side is also t. So I can say that the dimension on both sides are same, hence the given relation is dimensionally correct. So always try to write dimensionally correct. Do not write just correct. Then you have this assignment here, where just let me tell you this F represents force here. This S is again displacement. Initial or final velocity is v. U represents initial velocity. M represents mass. So you just need to check all the dimensions in all the terms, and you know how to proceed. This is again half mv square, where v is velocity, mass, acceleration due to gravity, and h is height. Height is like measurement of some length, so you have L, and this E is, let's say, energy. Then you must have come across this relation where we have this v as final velocity, u as initial velocity, 2 does not have dimension, a is acceleration, and s is displacement. So you should be able to do this 3. And finally this one, you will see that this is wrong. That means you're not going to get correct, but this is not a correct equation, because the dimension of this is not going to be equal to dimension of this. So you have to prove that. So you find the dimension on the left hand side, you find the dimension on the right hand side. A is acceleration, M is mass.